Welcome back to our lecture series on statistics for ENIGMA-U. This is part 2 of lecture 8, where we were just talking about independent t-tests, what they are, when to use them, how to use them, and how to calculate the t-values that will give us the results. Now, we are going to talk about the things that are important to report in addition to our t-test results. So, as a reminder, effect size is necessary to report whenever we're using hypothesis testing. The reason for this is because t-tests and any type of hypothesis test only tells us whether or not there is a difference between two means, not how big that difference is, and that's where effect size comes in. Effect size tells us it's how we measure how big a difference between two means is. And we have two ways of doing this for our one sample t-test, and they're going to be the same ways that we do it for our independent t-test. So the first way we do it is by calculating Cohen's d. This is a measure of effect size that tells us the number of standard deviation units by which the two means differ in this context. The formula here, in the context of an independent measures research study where we're using an independent t-test, the difference between the two sample means, this numerator here, is used as the best estimate of the mean difference between the two populations. And then the pooled standard deviation here, that's what this is called, or excuse me. Yeah, the pooled standard deviation right here, which is just the square root of the pooled variance actually, is used to estimate the population standard deviation. So that's what our formula looks like. And here are the size conventions for you to look at your leisure. The second way that we measure effect size is with R squared. This is how we measure what proportion of variance in our outcome is accounted for by the treatment. We talked about this in our last lecture about one sample t-tests, and the formula is for calculating R squared for an independent measures t-test is actually exactly the same as the way we calculate it for a one sample t-test. We take the square root, or not, excuse me, we square our t statistic in the numerator, and then we take that value and add it to our degrees of freedom in our denominator. And here are the size conventions. As a reminder, R squared, in other words, is the variability that is observed in the data that can be explained by the effect of the treatment. In other words, the size of our treatment effect. Let's look at some examples. So going back to the statistics that we gathered for our video games example in the last lecture, video games and SAT scores and stuff like that. If we're calculating Cohen's d, we're going to take the difference between our two means, and then we're going to also calculate the, excuse me. Oh my goodness. We're also going to calculate the pooled standard deviation. I forgot what that was called for a second. So the pooled standard deviation here is just the square root of our, oh my goodness, of our pooled variance here. Wow, excuse me. And then we're going to use that with the difference between our two means to get our d value of 0.67. And if we go back to our conventions, you'll see that this is a medium-sized effect of playing video games for 20 or more hours a week on SAT scores. We can also calculate effect size with our R squared value. And we're going to do that by taking the square root of our t statistic in the numerator, and then the square root of the t statistic plus the degrees of freedom in our denominator. And that's going to be 0.11, which is also a medium effect size if you look at the conventions for R squared. In other words, you could say playing video games for 20 or more hours per week in high school accounts for 11% of the variance between the SAT scores of the two groups. Okay, now we're going to talk about confidence intervals. This is the other thing that is really helpful when we're reporting the results of our t-tests. If you remember, in this context, a confidence interval is going to be the range of values that we estimate from our sample statistics with a given probability that the true value of the population parameter is going to fall within that interval. Instead of just centering our confidence interval around one sample mean to estimate one population mean, like we did in the one sample t-test, now we have two sample means and two population means to deal with in an independent t-test. So we're going to center our confidence interval around the difference between the sample means instead. And that will help us estimate what the difference between the actual population means is. So here is our formula that we're going to be using. The difference between the sample means plus or minus our t-critical value times the standard error of the difference between the means. So, and as per usual, the width of our confidence interval gives us information about how precise our estimate is. And remember, if the interval does not include 0, then we can claim that the treatment has a statistically significant effect. Let's look at an example. So if we were going to take a 95% confidence interval in the context of our video game example, we would say our alpha is 0.05, so we're going to use a 95% confidence interval. The lower limit we're going to calculate as the difference between the means minus our t-critical value times the standard error of the difference in the means. So the lower limit is 5.98. The upper limit is going to be that same difference, but plus this last part. And that's going to be 245.02. So what that means is we are 95% confident that the true difference between the population means falls within an interval of 5.98 to 245.02. In other words, if we repeated the same study many, many times, drawing a new sample from the population every time, the confidence intervals from 95% of those studies would include the true population mean. Now let's look at what happens if we were to get a 99% confidence interval. 99% confidence intervals is used when our alpha is 0.01. Remember, our alpha level has a direct influence on what our confidence interval is, because the percent confidence is 1 minus your alpha. And if your alpha changes, that means your t-critical value is going to change from our critical values table. So now if we do that same thing, calculating our lower and upper limits, we get negative 34.42 and 285.42, which means we are 99% confident that the true difference between the population means falls within an interval of negative 34.42 to positive 285.42. Because this confidence interval includes 0, it's from the lower to the upper limit, it spans over 0. We cannot claim that a significant difference exists at a two-tailed alpha level of 0.01, even though we could claim that a difference existed at a two-tailed alpha of 0.05. That's why it's important to be very, very precise when you're choosing your alpha levels. Lastly, we're going to look at how we report the results of an independent t-test in APA style. In this context here, you see we will often report our results in our results section. We talk about what type of t-test we're using. So a two-tailed independent t-test demonstrated a significant difference between SAT scores of those who played video games less than 20 hours per week in high school. And then we talk about the statistics of that group. The mean was here and the standard deviation was here. And those who played 20 or more hours in high school, a week in high school. We give the statistics of that sample with a medium effect size. Remember, we figured that out with our Cohen's d and our r squared. You say you give your t critical value, and within your t value, you'd say what your degrees of freedom were. You say your alpha level here, and then you give your Cohen's d, and then you state your confidence interval here. And again, just as a reminder, APA style requires us to report the exact p-value if it's less than 0.05, but greater than 0.001, but we're going to need statistical software to find it, such as Stata, which is something that you might come across as you're doing research in the real world, not just in this course. And Stata would tell us that our p-value is specifically 0.040. And then lastly, let's talk about some of the assumptions that we make with our independent t-tests. We assume that the dependent variable is going to be measured on an interval or ratio scale, that the independent variable is going to be categorical and has only 2 levels, because remember, we're only using 2 groups here, that random sampling was used to pick your samples, that we had independent observations when we were measuring our dependent sample, that we had homogeneity of variance, so the 2 populations from which our samples were being compared have equal variances. This, like it says here in bold, this is the most important assumption that needs to be satisfied when there's a large discrepancy between sample sizes. So you always need to check your variance. And then normality. The two populations from which our samples were selected must be normal. And with that, we are done with our lecture 8 about independent t-tests. In our next and final lecture, we're going to be talking about how to determine correlation and causation using statistics. So I will see you then.